Hello everybody. So here you have a dot, and the reason you have this dot is because it's as far as I got into recording this a second ago. This is even better dot. And then I went and ruined it. This dot is a ferrofluid. What ferrofluids are, and this is why normally videos like this where you're drawing to go along with things, don't operate in real time. Here is a beaker, and that is an incredibly bad beaker. That's a little bit better. Now, imagine you put some water in a beaker, and imagine, let's say this is the water, and you can see why I don't really do something like this, and now imagine that I dump some iron filings in the water. I shake the water up, and the iron filings all kind of float about. What I then do is I take a bar magnet, put it to one side, and what happens? Well, all of these, I'm almost certainly going to delete the water by accident when I do this. Hold it. Well, when I do that, all of the iron filings do kind of what you might expect. They become magnetized and they all go around to one side. So I began this by mentioning a ferrofluid. What happens here? Well, ferrofluids are a little bit weird. The way ferrofluids work is effectively when you zoom down, let's say that we've got a drop of ferrofluid in here. As I zoom down slowly more and more onto this ferrofluid, we eventually see that this ferrofluid is effectively the same thing. It's made up of, again, lots and lots of little, effectively iron filings. They're not iron filings, they're nanoparticles, but it's basically the same thing. They're magnetic nanoparticles. The one difference is that they're bounded to a surrounding oil-like solution. They're bound to some surrounding oil-like solution, and basically what this means is there's like actual complicated surface physics stuff to how they're bound to this, but in short what's going on is that they're connected to it. And what this means is that as I turn on, so this is without the magnet, now as I decide I'm going to turn on that magnet, this is going to move to one side. But unlike the iron filings, where the iron filings just ignore the fluid, instead, this time, the fluid and the particles within it move together. In this instance, they seem to have actually gotten larger, which they won't do. And the liquid will then stick to the edge of the container. Now, this in and of itself is, okay, you've just got a blob stuck to the edge of the container. But as it turns out, most of the time, you don't get a blob. If I kind of zoom in a little bit more on the edge of the container, in this case with a particularly large pen, because I totally forgot to change the pen, you'll see something where it basically looks like, okay, you have kind of the blob you're expecting to see. This kind of makes sense. But then some weird stuff starts happening on the edge. You get basically little pointy things. These little pointy things look something like this. And why am I talking about this? Well, in part, you may wonder why I'm talking about this on this channel. There's a reason this is called Ninja, and in short, it's because it's here for me to just post random stuff. As it happens, this is something I am basically working on at the moment. Actually, I possibly shouldn't have rubbed any of that out. This is something I'm working on at the moment as part of my degree. In particular, I do an experimental section, and this is what I'm doing for that, and I thought it would be fun to talk about. So, this is kind of the image of ferrofluids, that if you've ever looked up ferrofluid, or if you go and Google ferrofluid now, this is pretty much the sort of image you'll see. And there's then a bit of a question as to what actually makes it form this shape. Well, part of the answer to this question is the same reason why the ferrofluid was before just in a single circular droplet, and why it didn't go out to fill all of the water surrounding it. Why is this? Well, the reason this is exactly the same if instead of having a droplet of ferrofluid, I instead had some oil. If you've ever put vegetable oil and water in a cup and left them, you'll see that they separate out, they don't mix. And effectively, the reason they don't mix is because oil and water bond into very different ways. I'm getting more in depth in this than I really intended to, but water, wow, this is it's a very, very large pen. Water basically has an oxygen, and this oxygen is quite negative. It's going to have a tendency to pull the single electron from each hydrogen over onto it. It should probably have a couple of extra electrons there. It will have a tendency to pull those. No, those are involved in these bonds. It's been a while since I've done chemistry. If you want the diagram, looks something like this. In effect, the oxygen is going to basically steal the electrons away from the hydrogens. Electrons are negatively charged, which means you have a tendency to build up a charge, a negative charge in the oxygen, and you're going to tend to build up a positive charge, where it's the elementary charge, not the charge of an electron. It doesn't really matter if you are wondering. Water tends to build up charges like this. What this means is that, well, opposite charges attract, and therefore water molecules will have a tendency to line up something like this, where you have the negative and the positive attracting one another. These are known as hydrogen bonds, and they are particularly strong bonds. In fact, these hydrogen bonds are the reason that water behaves as it does, and they're the reason life on Earth exists, more or less. If you look at lots and lots of other well, specifically if you look down the group to try and predict what properties, what's oxygen? Group 6, group 7 on the periodic table? Don't remember. If you look at all the other things in that group, you'll see that oxygen has an abnormally let's get this. An abnormally low boiling point. High boiling point. Shoot. An abnormally high boiling point, basically meaning that the bonds are stronger and hold it together at higher temperatures than you'd expect. Hydrocarbons, on the other hand, don't have this, so these are your standard oils. What hydrocarbons basically have is you've got one hydrogen, you've got another hydrogen. They have some charge on them, but unfortunately your hydrocarbons are mostly covered in these hydrogens. Like this. There's no really spare room for... Wow, I just went off... Well, also went off the edge of my screen probably. For you guys. But there's no spare room for the hydrogens to interact with the carbon at the centre. So you've just got kind of a uniform charge distribution around the outside of your molecule. What this basically means is that you just have hydrogen interacting with hydrogen. The only thing that can happen here is, well, there's a little bit of mathematical subtlety to it, but effectively you can imagine it being the case that just by chance the electron in this hydrogen happens to be a little bit further over this side, and so you've got a slight negative charge on one side, slight positive charge on the other. If this does occur, then, well, you're going to get an induced dipole on the other one. You're going to have this is going to attract negative charge from this atom. It's going to pull over to this side, and you'll get a positive charge built up there. And so you have these kind of induced attractive forces, but because they don't naturally occur, they are significantly weaker. They're known as induced dipole interactions, or instantaneous induced dipole interactions, I think it is, or van der Waals forces. Now, basically, the difference here, there's this huge difference, and what this means is that if you put water molecules, which are looking at something like this, next to our hydrogen molecules, which usefully are drawn almost identically and without any consistent sizing, that would not be a H, that would be an O, and this has just got some hydrocarbon chain. Doesn't really matter what it does over here, who cares? All you need to know is that there are hydrogens on the outside and they're mostly uncharged. What this means is that these two things don't really interact with one another, and what this tends to mean is that if you mix the two of them up, you're going to get splitting, splitting into multiple layers, or at the very least, you're going to get almost bubbles, droplets of your hydrocarbon in the surroundings of the water. Now, what we've got going on here is almost identical. You've got your ferrofluids here in the surroundings of the water, and because they're immiscible, because of the structure, the ferrofluid as it happens is actually hydrocarbon based. Because of this, or the particular one we're using is anyway, because of this, you're going to have it tending to form a single droplet. But there are other things going on here, because, well, for starters, it's magnetic. So what we then see happening is effectively the material then also responds to not only the magnetic field of its surroundings, but also its own magnetic field. And this is what gives rise to these spikes. If I'm honest, I haven't worked through the maths on exactly why these spikes occur. My understanding, based on a very, very rough guess, is that you want to have as even a magnetization throughout your sample as possible. This is normally true for most things. You also want to minimize the surface area of your sample. Both of those any variations in the magnetic field within the sample and any extra surface area are both going to increase energy, and surfaces try and get into the position where they have the minimum amount of energy. That's why water does form a droplet. So what's going to happen here is, as you get closer and closer, if I draw on these magnetic field lines, as I get closer, magnetic field lines from within the material are kind of going to pull towards these points. Effectively, they're going to get more and more condensed, and this is going to happen as the magnetic field from the bar magnet decreases. So effectively, having these points means that the field is roughly constant. That's my guess, and the surface energy forces this to form like a single hole. So this is more or less, I tried undoing in the hope that I'd find something relevant. I didn't. So this was basically the project I signed up for. I signed up for a project on studying the shape of ferrofluids and how they form shapes. It's a non-linear process, which is really cool. Don't get to work with those very often. And how they form shapes under magnetic fields. Unfortunately, I was entirely wrong as to what it was I was going to be studying. As it turns out, we are dealing with ferrofluids under magnetic fields, but instead we're taking two slides like this, we're putting a drop of ferrofluid between them, we're then moving this layer down, so we get something like this. So we're just sandwiching this drop in between two layers. I'm going to inject something, it's a solution known as Triton X, which I believe is hydrocarbon based. It's different hydrocarbon from the ferrofluid, so the ferrofluid doesn't dissolve in it, but it basically controls how miscible the two are, and how likely one is to mix in the other. And effectively, what controls how well two things mix is the energy it takes to form a surface between them. This is why surface area to volume ratio in stuff like raindrops is particularly important, which is why raindrops tend to form spheres. And yeah, they do form spheres, not this. They only form that shape when they're actually dripping out of a tap. But you very rarely see a raindrop in freefall. You almost always see water when it's dripping off of something, which is why we tend to draw them like that. So this is the system we're looking at, and effectively, because these spikes are due to simultaneously considering the surface tension, or the surface energy, the area around here, around the side, and the amount by which you need to condense the magnetic field, the surface energy is going to play a huge role. The amount you're penalised for adding extra surface area, because again, that's the reason why things tend to form spheres, because the more surface area you add, the more you're penalised for it. And in the case of raindrops, that's all that matters. In the case of ferrofluids, you've also got magnetic fields, and you've got the energy of the magnetic field to worry about. But the point is, adding this solution gives us a little bit more control of the surface energy, and it's something I'll be working with later on. For now, The next step is to do what you probably always are going to want to do with a ferrofluid. Add a magnet. Actually, I'm not quite adding a bar magnet. This is a bit of a lie. I don't have anything that's particularly copper coloured, so I'm going to use a rainbow coloured pen because that makes me happy. I'm going to add one coil beneath here. Going to add one coil up here, and these are going to generate a magnetic field. In fact, the magnetic fields they're going to generate, it will bulge out a little bit, but it's actually pretty uniform right in the middle. And so you're going to be chucking your droplet of ferrofluid into an approximately uniform magnetic field. And when you do this, something really cool begins to happen. Initially, I'm going to start with a droplet that looks something like this. It's going to be more circular, but unfortunately I'm not very good at drawing circles, and I'm doing this live. I realise there is a shape tool on OneNote, I guess, but I'm lazy. Initially it begins circular. Then, slowly as I increase the field, well, I'm going to see it beginning to bulge out. It was already quite bulgy because of how I drew this, but I'm going to see it bulge out. I'm going to see it become more elliptical. It's also getting thinner down here, but if I use the eraser tool, it will just erase all of this, so I'm not doing that just yet. So it begins to, well, initially it does nothing, but then it begins to bulge out. And shortly after it bulges out, it then begins to take on a dumbbell shape. It may take on a dumbbell shape with two dumbbells, but it doesn't always. I'm going to stop filling this in very carefully because I'm just going to need to get rid of it again. In fact, one of the ones I did earlier today did something like this. And then as you continued, it began to be a little bit more like this. And you just kept going, and what would happen is it effectively branched out into what are typically called arms. And this is really typical behaviour. As you slowly increase the magnetic field on one of these things, it will branch out. And so you'll begin with something that maybe looks like just a drop, but you end up with this really cool, what's known as a labyrinthine structure, where it kind of goes, let's say, something like this. I don't know. And you have, I'm doing this and yeah, it's looking a little bit suspect, but yeah, as I do this, it continues to branch out, and the branching out happens in typically quite a regular pattern. And so my challenge is basically to look at the structures these form. Now, the first thing I did was, well, just try and put things between two plates. Our setup looks something like this. We've got a camera up the top. We've got our loops of wires here and here. We've got a big thing, big thick metal thing to mount. We've also got a light going up through the bottom of this, which is shining light upwards into the camera. This camera is connected up to a laptop over here. And we're going to have our layer of ferrofluid about here. Something like that. And then our droplet sitting right in the middle. Now, turns out, this stage, the getting the ferrofluids droplet in between two plates is really, really kind of non-trivial. In fact, basically what I need to do is we need to, first off, there is a lot of cleaning out sample holders in this, as it turns out that is the majority of science. We've got a sample holder, it's kind of multi-layered, probably won't come across very well in this drawing, but there we are. And firstly, I need to insert a glass pane basically at the bottom, at this bottom area here. Then I'm going to, there should really be another step here, but effectively I'm then going to insert a glass plane. After that, I insert a glass plane over this entire top area, and I will have my Triton X solution in the middle and my ferrofluid droplets sandwiched in between these two. And I can, depending on the height I want to get, I can use different sizes of these. Each one has a thing that says it was something like a stupidly high number of decimal points on this, like I'm sure far more than they can justify, or maybe I just missaw the thing that was being used. But yeah, the challenge is initially you need to wash this, which is more annoying than it sounds. Like, washing oily stuff is always troubling. We do have ethanol, which makes washing oily things easier, but the ferrofluid is still, it gets everywhere. You also need to begin by taking one of these lenses, and you need to ensure that this lens is as clean as possible. This isn't actually, sorry, this is called a lens. They got me into the habit of calling it this. I mean, technically it is a lens, but only insofar as anything glass is a lens. It's a lens that focuses rays from infinity at infinity. It has an infinite focal length, which arguably isn't that useful for most lenses. It's just a plate of glass. But what we need to do is we need to clean this, and the reason we're cleaning this has nothing to do with image quality. It's not the fact that if there's a tiny bit of dust on the lens, we won't be able to see what's going on, because, well, actually, the size of this structure is relatively large. It's on the scale that you could see it with the naked eye. And so that's not really what's going on here. The reason we're concerned about it is because, well, so much of this stuff is to do with surface energy. And what will happen is, if I have this lens, if I cover it mostly in my Triton X solution, I then drop my ferrofluid right in the center of it. And let's say that I somewhere have a tiny fiber of some sort. What's going to happen is the ferrofluid will essentially just cling to that fiber. It will have a tendency to just stick to it and go nearby. In fact, it's not just fibers it does this with. Even if I wish I had a white pen available, because that'd make this a lot easier, but one of the reasons this might be in this particular position to begin with is if, say, there was an air bubble. Yes, I just drew an air bubble in purple. Yes, I know that makes no sense and it should be in white, fight me. But yeah, even if there's an air bubble, your ferrofluid will have a tendency to stick to it, because we're just working with something at that smaller scale where surface tension really plays an important role. It's just as though if you touch a water droplet, no matter how light a touch you give to it, the water droplet will jump up and touch your finger. Or if you've got a toothpick or even a needle and you poke it with a water droplet and you pull the needle out, actually beneath a certain scale this tends to happen less, but I think with the toothpick, actually, the material also makes quite a large difference. There are things I'm thinking about as I'm saying this that means it's less general, but the point still is, if you poke something, if you poke a droplet, it will tend to respond. If I poke a water droplet, we'll probably have a tendency, if I'm poking it with something sharp, it will have a tendency to bend inwards a little bit as I poke sharp thing into it. And effectively, and as I pull it out, it will do something like this. And it will stick to sharp thing. And so basically, even small things can cause droplets of the ferrofluid to stick somewhere, which is quite problematic. And so you've got to be very careful ensuring that nothing gets lost, nothing comes off of whatever you're using to clean the lenses onto the lens, because it's all very well, we can clean it with ethanol, and that will get off pretty much everything, but it won't get off stuff that you're actually dropping on with the lens cloth you're using. We're using particular like lens wipes, but even they will like deposit small fibers, or maybe it's not them, it's just the air, and they'll deposit small fibers, and then you have to get those fibers off. But how do you get it off? Well, you need to use a lens wipe, and then you get into a little bit of a loop where you're just maybe removing two fibers and depositing one every time. Eventually, you get something that looks quite clean, and the challenge is now, okay, you then apply some grease. Here, this is just to prevent any of the solution running out, because if I were to just chuck the glass plate in, and in fact this is what the person demonstrating the project did, to begin with, if I just put the glass plate in and hadn't put any grease there, then the Triton X would just flow out around the edges and it wouldn't work. The grease creates a seal, which is all well and good. We then pour on the Triton X, we then take our ferrofluid droplet, put it in the centre, and we then have to get on a second glass slide over the top. The issue is, if we're trying to do this, that I've actually already messed up. What I really want to do is I want to ensure that I'm going to put another glass slide over the top. However, as you're probably beginning to realise, surfaces are incredibly important, and what I want to ensure is that this surface is already covered by the Triton X. So what I actually do is I put this on top of here to ensure that the Triton X is covered up, or is the Triton X that's already sitting in the bottom of this is now fully covering this top plate, and then I lift that up. So I put it down, I then lift it up, I then, whilst holding it up, kind of like this, with a toothpick, I don't know, red. With a toothpick here, whilst lifting it up, I then quickly attempt to, I'm definitely running out of colours. Yeah, I've already used that one. Shoot, that's my grease. No, I'm out. I then attempt to inject my ferrofluid into the centre, and then, removing my toothpick, drop the lid back down, and hope that throughout all that process no air bubbles formed. Unfortunately, what kind of happens is there's a tendency, as I slowly put this lid down, there'll be a tendency to be, there's actually a small step about here, which I'm putting it down on, it's just hard to draw. And what will happen is if you've put enough Triton X to cover up the bottom bit, there'll be some overlapping this step. And as I slowly lower the lens down, effectively, as I lower the lens, it pushes the Triton X around... what's Triton X? It pushes the Triton X around here further than, like, the layer of the Triton X at the bottom. Wow, this diagram is becoming impossible. It pushes the Triton X further than, like, the layer of Triton X at the bottom is, because you're actively pushing the Triton X, which is here. As you push down, it has to go somewhere, and it can't go this way. So it will have a tendency, and there'll be and some of it will go down this way, but some of it will also go this way. Whereas you're not actively pushing down on the Triton X at the bottom, which basically means that it tends to basically race me around, and the Triton X tends to get all the way around the edge before all of the Triton X on the bottom layer has actually touched the top, meaning that I tend to get air bubbles, which cause problems. All of this, as you may be beginning to realise, is a little bit of pain. I've actually done so much that I can't undo far enough. So let me just quickly delete everything I've drawn. What I ended up with on my first attempt was really awful. I basically ended up with a slide that, when I looked at it under the camera, looked something like this. There were lots and lots of kind of small dots of my ferrofluid solution. However, the only reason I'd actually done this run was solely so that I could get that was attempting to be me just colouring the rest of the glass, not crossing everything out. But the only reason I actually did this was to work out effectively how far down from my camera this actually was, to ensure that I could focus my camera up here on this correctly, and I could adjust all my settings. Once I'd done that, well, this particular run through didn't really matter. There were still other things I had to calibrate. And so I basically, mucking around, turned on the magnetic field, and something quite cool happened. I was zoomed in on one particular dot, because what I wanted to do was consider the very smallest dot I could find and try and ensure that was focused as well as I could possibly focus it. But what I noticed is that as I did this, these dots, this is now no longer representing the magnetic field, these dots began to move. Initially they all began to move towards the centre, which was kind of expected. You tend to expect things to move in such a way that maximizes their magnetization, because effectively, if I have a magnet here, it's my north pole, it's my south pole, I have a chunk of iron that might be off the side, so I'll do it here. If I have some chunk of iron up here, well, the south pole is going to attract north poles within this magnet and will repel the south poles, and therefore, even though this wasn't magnetized to begin with, it will become magnetized. Just as with the hydrogen atoms earlier, you get this induced effect. And what was happening here is that magnetic moments were being induced in all of these, and they were pushing them towards the centre, which I kind of expected. But what I didn't expect was the fact that, well, they didn't meet at the centre. In fact, what actually happened was something that looked a bit like this. We formed something that was pretty hexagonal. In part, the reason this isn't perfectly hexagonal is just due to my bad drawing, but some of the things in here were actually intentional. These smaller dots are closer to the central dots, these larger dots are a little bit further out. What's going on here is that, effectively, what's happening is we're, from beneath, turning on a powerful magnet. What this does is it turns each of these into magnets themselves, but it doesn't turn them into magnets like splitting them like this, north and south, because that's not the direction the magnetic field's being applied. Instead, it turns them into magnets which look like south and north. But if you've ever taken two magnets that look like that look like this, NS, and put another one right next to it, I'll give myself a little bit more room to do the letters this time, you'll know that they don't really like being that way around. They repel one another. In fact, they far prefer to be like this. Unfortunately, here, this magnet at the bottom is forcing exactly how they're going to be. They are going to be like this. They don't have much of a choice about it. And so what happens is that these two magnets are going to experience a force that effectively means they repel one another. They both move away. And the larger every single little droplet is, the larger a magnetic field it exerts on those surrounding it, the more it pushes away, hence we get this design. The reason we got a hexagon was simply the number of droplets I had and the fact that the hexagon formed the minimum energy configuration. So that was kind of cool, and it was also really interesting because one of the early papers on this had noticed that if you had a structure that looked something like this, one of those 3D ferrofluid structures, not when we're just crushing it between two plates and getting it something different because of that these spikes tended to form hexagonal structures. So this was quite nice. It was almost as though we'd just taken this and we'd decided, no, I'm just going to cut the top off. And you should expect there to be some analogy between the two. It's not perfect, but you certainly might expect there to be some analogy between the 2D and 3D case. And the fun part of this for me is that it actually kind of begins to predict a little bit of the stuff we're going to do later on, because if I have kind of something branching out in multiple different directions like this, well, the corners tends to have a little bit more stuff, and the ends also tend to have a little bit more stuff to them. And this then gives us a little bit of information. There was a little bit of information as to how these should be spaced given their sizes, which I think is quite interesting. We also discovered some other stuff mucking around in the lab, because today we were basically just trying to get our technique down and trying to improve our technique. One thing we noticed is that if we actually, let's put all that back. If you do start with this, and you really, really, really rapidly turn off the field, what you actually get is all of the little arms retract in on themselves, and you effectively split this up into some slightly larger droplets. Not larger than the ones that started with, but larger than like the small nodes that were on the edge of each one, because all the fluid has gone back into them, which was relatively interesting. It meant that like the speed at which we changed the field actually made quite a large difference, which was fun. So yeah, I don't know. Wanting to do something on this because yeah, it's kind of a cool thing. I'm interested to be looking into it. That said, thank you all for watching. Been Intravel you, and I'll see you around.